Welcome everyone to our presentation on noise shaping SAR ADC. Before moving into noise shaping SAR ADC, let's look at the baseline, the standard SAR ADC. The standard SAR ADC is a very popular one because it's being used in many places like the regular MCU or FGS and other places. Because the standard ADC has several advantages. The first one is it's highly energy efficient. Second, it's heavily digital, so it scales brilliantly with modern CMOS nodes. But it has a hard ceiling. Usually, SAR ADC is okay with 10 to 12 bits effective number of bits. That's enough for many cases. But if you really want to push that to 14 or 16 bit, the math turns against its design. Let's look at why on the next slide. So what builds those resolution wall? There are three main reasons for that. The first one is thermal noise. Because everything in analog world is bounded by thermal noise. Usually to decrease the noise to half of the original noise, we have to increase the capacitor sizes 4 times. That will result in larger layout areas and also the switching power loss. So while we increase the capacitor areas to 4-fold, we are also increasing the switching power loss also. So that will lead to massive footprint area and severe driving power needs. Okay. The second one is comparator noise. So to resolve those tiny bits, while we are going for 14 or 16 bit of effective number of bits, we really need to compare voltage differences that are in microvolt levels. So to resolve those tiny bits, we really need to have low noise comparators. But those low noise comparators are very power hungry. So that's also not beneficial for our ADCs. Then finally the deck mismatch. Usually for 14-16 bit resolution, we really need to have large number of capacitors, and designing those with precise accuracy, we have to look on severe capacitor matching techniques. If we fail to do that, then that will result in non-linear responses. Okay, so these are the main reasons that SAR ADC fails at high effective number of bits. Okay, so this is where we introduce the cheat code to overcome this trade-off. So what we are doing is we are borrowing the oversampling of signal from the delta sigma ADC and apply a noise transfer function to it. So take a look at on this equation where we can see we are having the quantization error and applying a noise transfer function to it. By doing this, we are really pushing the noise out of our signal band. So this acts as a high pass filter for the quantization error. By doing this, we could be able to achieve higher signal to noise ratios with a simple comparator and smaller capacitor sizes. So what we are doing is we are oversampling the signal, like in the delta sigma modulator, we are oversampling the signal and having the normal SAR in the core. So by doing this, we could be able to achieve higher resolution with low power consumption. So that what is noise shaping ADC really. So I welcome Ahmad to explain the rest. Over to you, Ahmad. Thank you.
Thank you, Rajinder. Now, I am going to talk about core architecture and operating principle of a noise shaping SAR ADC, also known as NSR ADC. This architecture combines the advantages of two popular ADC types. One, the SAR ADC, which is simple and power efficient. Second, the delta sigma ADC, which provides high resolution than through noise shaping. The key idea behind this is instead of wasting the quantization error after each conversion, it reuses that error to improve accuracy in the next stage. This allows high resolution with very low power consumption. If we talk about error feedback topology, at the end of every SAR conversion, the core insight is at the end of every SAR conversion, the DAC naturally contains a small remaining voltage called residue voltage or residue quantization error. This traditional delta sigma ADCs usually require dedicated subtractors, large analog summing nodes, and highly linear op-amps. These increase complexity and power consumption. However, in noise shaping SAR ADCs, we directly reuse the natural residue already available in the DAC. So the system only processes tiny error signals instead of the full-scale analog input. This is the main reason why NSR achieves excellent efficiency with simple analog circuitry. Now we talk about why noise shaping SAR is more power efficient. Traditional delta sigma architectures, as you can see, process entire analog signals continuously, which requires complex analog blocks and high power. And in contrast to noise shaping SAR ADC, the noise shaping SAR ADCs reuse the natural DAC residue, process a small amount of error signal, and use minimal analog circuitry. So the residue voltage is given by voltage of residue is given by the input voltage minus voltage of DAC. The residue is much smaller than the original signal, so the ADC can achieve lower power consumption while maintaining high dynamic range and resolution. If we talk about the operating cycle, there are four main stages. First one is sampling, second one is SAR conversion, third one is residue extraction, fourth one loop filtering and feedback. The important principle here is that the quantization residue from one conversion cycle is reused to improve the next conversion cycle. I'll briefly explain each stage now. Sampling phase. In the sampling phase, the analog input voltage is sampled onto the capacitor DAC array, also called as CDAC array. The capacitor array stores the analog signal as charge before conversion begins. The stored charge follows the relation Q is equal to C multiplied by V input voltage. This phase establishes the initial charge distribution required for the SAR conversion process. Next, if we talk about conversion phase, SAR conversion phase, here the ADC determines the digital output 1 bit at a time, starting from the most significant bit or MSB down to the least significant bit LSB. The comparator checks whether the DAC voltage is higher or lower than the input signal, and based on that decision, the CDAC updates its voltage. This process is essentially a binary search that gradually minimizes the conversion error. Compared to a flash ADCs, this method is much more power efficient. Next, the residue extraction. This is the most important step in the noise shaping SAR architecture. After the final bit decision, a very small voltage still remains on the DAC capacitor array. This remaining voltage is called the residue voltages. In conventional SAR ADCs, this residue is simply discarded. But in noise shaping SAR ADCs, this residue is preserved and reused for noise shaping. That reuse is what improves effective resolution and reduces in band quantization noise. Now, if we talk about loop filtering and feedback, in the final stage, the extracted residue is sampled and passed through a loop filter. The loop filter integrates the error and feeds it back into the comparator during the next conversion cycle. This feedback process shapes the quantization noise so that most of the noise is filtered and shifted outside the signal band. As a result, in-band noise decreases, dynamic range increases, and overall ADC resolution improves very much. This noise shaping mechanism is what allows noise shaping SAR ADCs to combine high accuracy with lower power consumption. Now I invite Kavishka to explain the next part. Thank you.
Thank you, Ahmed. So let's dive into loop filter implementation, which is the engine that drives the noise shaping SAR ADC. The filter's core job is to integrate the residual voltage left on the DAC array and use it to shape the quantization noise away from our band of interest. As circuit designers, we have faced a fundamental architectural choice to achieve this. Do we implement a passive loop filter or do we go into an active loop filter? Let's trace the flow of how these two options perform and see how to make the right decision and the design choice. The first method, the passive approach. So if we look into the passive approach, the mechanism is elegant in its simplicity. The filter is built entirely out of switched capacitor networks and CMOS switches. Because there are no amplifiers, the immediate massive advantage here is the zero static power consumption. It only draws dynamic power when the switches play. On top of that, because it relies on capacitor ratios rather than transistor transconductances, it scales beautifully with the modern CMOS nodes and remains highly robust against the process, voltage, and temperature variations. However, the laws of physics catch up with us during the charge sharing phase. When the transferring of the charge between the passive capacitors, we inevitably lose signal energy. This means the filter gain is inherently less than 1. And it makes it impossible to achieve a perfect mathematical integration. As a result, the noise shaping capability is weak and it usually is limited to first order or a mild second order noise transfer function. If your system requires aggressive noise suppression, the passive charge sharing alone will simply won't give us the effect. So for that, we have the active approach. This brings an active alternative. To overcome the lossy nature of the charge sharing, we introduce active gain elements into the loop, such as operational transconductor amplifiers, which means OTAs, or ring amplifiers, inverting amplifiers, things like that. By adding this active amplification, you can achieve a true high gain integration. So this unlocks a sharp, aggressive noise shaping, making third order or even fourth order transfer functions highly achievable. If your target is a demand that needs high dynamic range and an SNR of 80 decibels or more, active integration is virtually mandatory to deeply suppress the in-band noise flow. But this performance boost comes at a steep cost. Active filters consume continuous static power, and also it requires rigorous frequency compensation to maintain loop stability and present severe design bottlenecks when you try to scale down into advanced low voltage nodes where transistor headroom is highly restricted. So, when we are comparing the two active and passive loop filtering, how do we choose one? The design flow comes down to the application's power and performance budgets. If you are designing for ultra low power IoT or biomedical devices where a moderate SNR is perfectly acceptable, the passive loop filter is the best choice because it is stable, low power, and highly stable. On the other hand, if you are targeting into high performance audio like communications, applications which demands maximum SNR, you have to opt out for the active architecture. So to wrap up, it is worth looking at where modern industry research is heading. Designers today are fighting to get the best of both worlds. The current trend is to replace those power-hungry continuous time OTAs with highly efficient dynamic amplifiers, especially ring amplifiers or floating inverting amplifiers. These structures provide high active gain needed for the deep noise suppression, but also they only draw current during clock transitions. Essentially, they deliver active level performance at near passive power efficiency. So that's about choosing between the active loop shaping and the passive loop shaping. To continue on, I hand over this to Anjana.
Okay, thank you, Kavishkar. In my next slide, what I'm going to talk about is how to tackle the mismatch in capacitors. Noise shaping is a good at reducing noise, but it has a big blind spot. The tiny capacitors inside deck are perfectly identically coming out of the factory. Those small mismatches gives errors in noise shaping. So the IC designers have to use some methods to improvise that. So they have used two methods. First one is dynamic element matching and second one is data weighted average. So what they have done is they are taking turns using each capacitors. So no single bad one dominates. The error gets spread out and pushed to frequencies that the filters throws away. So simple idea but big impact. On the next slide, what I'm going to talk about is I'm going to talk about the trade-off. So oversampling gives you better resolution, but it slows you down. So what if you need both speed and resolution? So IC designers again have to come with two methods. So first one is time interleaving. It's like having multiple checkout lines at a supermarket. So the several noise shaping SAR ADC cores work in parallel and you combine their outputs. Then you get the same high speed without sacrificing the quality. And the second one is multi-stage noise shaping. So this tackles a different issue. High order noise shaping is in a single loop tends to go unstable. So like feedback screech on a microphone. So you get the same aggressive noise reduction without instability risk by using this. So in my next slide, what I'm going to talk about is I'm going to talk about some applications that our noise shaping SAR ADC use. So when we are going to talk about biomedical and wearables in your smartwatches and your ECG patches, it only has a small tiny battery. But when we are talking about the power, we have to consume a lot, like a very small power for that wearables. So noise shaping SAR gives a medical grade accuracy at almost no power cost. And when you're talking about robotics, a tactical sensor array need one small low power ADC per each sensor node. So noise shaping SAR fit perfectly into that kind of dense compact system. And when you're talking about software defined radios, 5G, 6G radios, the time interleaving noise shaping SAR approach from my previous slide is exactly how the modern wideband receivers are built. And when we are going to the conclusion, so the noise shaping SAR is basically took the best parts of two old ADCs. First one is SAR ADC, second one is Sigma Delta ADC. When we talk about the SAR ADC, it is mainly popular for speed and low power. And when we are talking about Sigma Delta ADC, it's very popular for the resolution. So when we are using a ADC we want both speed, low power, and the resolution. So what we are going to do is we are going to combine those two ADCs and make noise shaping SAR ADC. So the secret is very simple. What we are trying to do is we are integrating those architectures and adding a simple feedback loop. So with that feedback loop, it's like learning the own mistakes each cycle and correct them in the next cycle. So that's why it's had a big impact in a short time. So that's our presentation on noise shaping SAR ADC. Thank you everyone for listening that.